Okay, so we're going to prove that this sequence xn forms a set that is dense in the interval 0 to 1. And so xn is defined to be, for some irrational number r, it's all of the positive integer multiples of r, and then you take the fractional parts of those. Okay, so we have two facts that we're going to use. One that you can try proving is that for distinct indices, these numbers are distinct from each other. So this is basically saying that if I take the fractional part of Rm, and then I take the fractional part of Rn, as long as m and n are distinct, these are not equal to each other. Okay, and then the second fact is a fact about fractional parts. And this is that fractional parts basically distribute across the difference of two numbers. Right? So as long as x minus y is a positive number, then this equality holds. Okay, so proof. So the first thing we're going to notice is that all of these numbers xn lie in the interval from 0 to 1. And so in particular, that means that the sequence xn is bounded. So because it's bounded, there's a subsequence, x and k, of xn, which converges. And in particular, x and k is Cauchy. Okay, so what that means is that there exist I and j integers distinct from each other, such that if we fix epsilon bigger than 0, then xi minus xj is less than epsilon. And, without loss of generality, we'll just assume that xi is the larger of the two numbers, and so this is bigger than 0. Okay. So we want to use this. One thing we can notice is that if we define y to be this difference, xi minus xj, we know that y is less than epsilon. And so if you break up the interval from 0 to 1, right, you can imagine I can kind of break this up into, there's like the interval from 0 to epsilon, which is where y is. Then there's the interval from epsilon to 2 epsilon, and then ... And every number in the interval from 0 to 1 lands in exactly one of these intervals, right? And I know that because y is less than epsilon, every multiple of y falls into each of these intervals at least once. So there's a positive integer multiple of y, at least one of them in each of these intervals. Right. So what that means is for all, call them x in 0, 1, there exists a positive integer k such that k times y, or the absolute value of k times y minus x, is less than epsilon. So this is kind of close to what we're trying to show already, because we're trying to show that the elements of the sequence xn are dense in this interval, and we already showed that we can approximate numbers in the interval from 0 to 1 by multiples of this number y. Okay, so we're pretty close, but now we want to notice, if we look at what the definition of y is again, that this is xi minus xj, and that's the same as just the fractional part of ri minus the fractional part of rj. And so using our fact before that the fractional part distributes across these differences, this is equal to k fractional part of ri minus rj, and then that's equal to k fractional part of ri minus j. Great, but we can assume, we can kind of add in the further assumption here that ky is less than or equal to 1. And if this is true, then k times the fractional part of this is also going to be equal to the fractional part of kr times I minus j. Right, so you can bring the k to the inside. And the reason that you can do that is because by assumption, this expression is less than or equal to 1, and so it's equal to its fractional part. So you can just bring the k inside of the fractional part. But then notice that by definition, this is just x sub k times I minus j. Right, so this is actually an element of the sequence xn that we started with. And so what do we have? We have that for all x in the interval from 0 to 1, there exists an element of the sequence, like this, such that the difference between that number and x is less than epsilon. And that's the same as saying that the sequence xn that we started with is dense in this interval. So that's it.